For Sam's and I's final project, we are looking at the physics behind a rotating ball and baton and its motion. So as you can see, I have a picture of the baton and its VZ initial, its VX initial, and its omega initial, and its VZ final, its VX final, and the omega final. So first, I solve for conservation of momentum, starting with this equation, and with substituting the I in as 1/12 ml squared, and plugging that all in, we are left with ml times Vx initial minus Vx final equals 1/12 ml squared omega final minus omega initial. As you can see, the ml's will cancel, and we are given the equation Vx initial minus Vx final equals 1/12 L times omega final minus omega initial. Moving on to our conservation of energy, we have kinetic energy plus the rotational energy. As you can see, this is the equation we used, and we did some substitution, and we were left with Vx initial squared minus Vx final squared equals 1/12 L squared times omega F squared minus omega initial squared. Taking this equation, we could substitute these two values into Vxi initial minus Vx final times Vx initial plus Vx final, and omega final minus omega initial times omega final plus omega initial. And then we can divide the conservation of energy by the conservation of momentum, and we are given the equation Vx initial plus Vx final equals L times omega final plus omega initial. And with this equation and the conservation of momentum, we can solve for Vx final and omega final, and that way we can test the length, the Vx initial, and also the omega initial to see what the baton would do when you spin it. So now that we have the conservation of momentum and the conservation of energy, we can add those equations together, and we get 2 Vx initial equals 13/12 L omega final plus 11/12 L omega initial. And then now we can solve for omega final, which we are given right here, which equals 24 Vx initial over 13 L minus 11 omega initial over 13. We can plug that in to our equation to solve for Vx final, which is going to be 11 Vx initial over 13 minus 2L omega initial over 13. So now we can see with this equation what will happen if we throw and spin a ball. So we throw at a speed of 1 meter per second, or a baton, and our length will be 0.25 meters, and our initial angular momentum is going to be 22 seconds. So we have Vx final equals this. So that's going to be 11 times 1 meters per second over 13 minus, I'm going to write it down here, 2 times 0.25 meters times 22 seconds, all over 13. So our Vx final is going to equal 11/13 meters per second minus 11/13 meters per second, which is going to equal 0 meters per second. And now that means that the ball was spun and thrown so perfectly that it hit the ground and it bounced straight up. Boom.
Now talking about a sphere like a basketball, our conservation of momentum equation is given here, and we know that the angular momentum of a sphere is 2/5 mr squared. So if we plug that into our conservation of momentum equation, it gives us this 2/5 mr squared omega I plus mr Vxi equals 2/5 mr squared omega final plus mr Vx final. And if we get all the velocities on one side and all the angular velocities on one side, we get this equation. And then we want it to be final minus initial, not initial minus final. So our equation is velocity x final minus velocity x initial equals -2/5 r times omega final minus omega initial. And that's our conservation of momentum equation. Now talking about conservation of energy, our equation is here. But since Vz initial equals the opposite Vz final, our z directions cancels, which just gives us 1/2 mvx squared plus 1/2 I omega initial squared equals 1/2 mvx final squared plus 1/2 I omega final squared. Putting all the velocities on one side and all the omegas on one side, multiplying by 2 and dividing by m, we get this equation. And again, we want final minus initial, not initial minus final. So we're given the equation velocity of x final squared minus velocity x initial squared equals -2/5 r squared times omega final squared minus omega initial squared. And because of the identity that a squared minus b squared equals a plus b times a minus b, we can rewrite this equation as this: vx final plus vx initial times vx final minus vx initial equals -2/5 r squared times omega final minus omega initial times omega final minus omega initial. And if we take that equation of conservation of energy and divide it by our equation of conservation of momentum, we are given the equation Vx final plus Vx initial equals R times omega final plus omega initial. And these are our two equations that will help us solve for omega final and Vx. Using our two equations of conservation of momentum and conservation of energy, if we add those up together, we get that the front of the equation gets us 2 times Vx initial, which will be the front end of our new equation, as you'll see. And if we add up the second parts of both equations, we get R times 3/5 omega final plus 7/5 omega initial. And we set those equally to each other. So 2 Vx initial equals R times 3/5 omega final plus 7/5 omega initial. And from there, we're trying to solve for omega final in terms of Vx initial and omega initial. And through a ton of algebra, we get to omega final equaling 10 Vx initial over 3R minus 7 times omega initial over 3. And now solving for Vx final, we can do the same thing, but what I did here is I multiplied the equation of conservation of energy by 2/5 so I could cancel out omega final. So the front end is equal to -3/5 Vx final plus 7/5 Vx initial. And adding up the second parts of both equations, you get 4/5 R times omega initial. And so if you set those equally to each other, and then algebraically solve for Vx final, you get Vx final equals 7/3 Vx initial minus 4/3 R times omega initial. So these are two functions that get you omega final and Vx final in terms of Vx initial and omega initial. So if a problem were to ask what is the final angular velocity given R, which is just the radius of a basketball, which I looked up, and it's 0.12 meters. And if you were to throw it at a initial velocity of 1 meter per second, and with a initial angular velocity of 11.9 radians per second, you plug those in all into your equation of omega final, and you get that it equals 0, which means that after it bounces the first time, it will stop spinning. Now this means that you will probably have a Vx final, which you could conveniently solve for using the other equation.